So this is, in fact, Felix Bloch again, and this is Ed Purcell, and we're back in 1952. And I would like to think that Felix Bloch is smiling a little bit in that picture, but I think I'm not sure. He should have been alive by the time that prize came out. Well, now I'm going to really shift gears and talk a little bit about my own contributions to science. And I suppose the person that I have the most to thank was my chemistry teacher, shown right here. This is William Hawke, and I dare say that the first large prize I got was a MacArthur Prize. And I called him up on the phone, and I said, I hadn't seen him for many years, and I said, Mr. Hawke, guess who? And he said, well, that has to be Douglas Osheroff. I think he'd read that I'd gotten this prize and thought I might call him up. Anyway, so this is William Hawke, and this guy that's looking over his shoulder, that's me. And I dare say that the next three people, these were guys we were partners in crime. We liked to make bombs and rockets, things like that. So we did a lot of that sort of thing. This is Al Close, who was my debate partner in high school. I was not a very good debater, I'm afraid. I didn't do my homework well, but we managed to win our share of prizes, I suppose. Okay, so then I'm blipping over my 4 years at Caltech. I actually was involved in astrophysics when I was at Caltech, mostly. Infrared astrophysics was a new field, and so when I applied for a graduate study, I actually applied only to schools that had good astrophysics programs. And then, as I was, I think I applied to 8 schools, and I got accepted to all 8 of them. But then I started thinking about what I loved doing with my life, and it wasn't observing some objects that were so far away I couldn't possibly touch them. But in fact, I really liked to do experiments. And so in the last moment, I switched, and I decided to go into condensed matter physics, as you heard. So I went to Cornell, and that as a graduate student, and I was teaching for David Lee, who ended up being my PhD thesis advisor. And this was just at the time that new refrigeration technologies were being developed. So this is something called the helium-3, helium-4 dilution refrigerator, and I won't explain all of it. This is actually a picture of my helium-3, helium-4 dilution refrigerator. This is where the cooling occurred, and then these are heat exchangers which would use the rising cold helium-3 liquid to cool a returning helium-3 returning to the mixing chamber. So this was my device, but when I was at Cornell at that time, every graduate student was building their own dilution refrigerator. Mine was one of the ones that actually worked, which was a good thing for me, anyway. So, but in fact, there was another technology. So what had happened was helium-3 and helium-4 are, of course, both isotopes of helium, but helium-3 is extremely rare. It essentially doesn't exist naturally. The amount of helium-3 in natural gas wells, which is where you get most of the helium-4 from, was vanishingly small. However, helium-3 results from the decay of tritium. And so during the period after World War II, where the US and the Soviet Union were busily building hydrogen bombs, they were creating tritium, and tritium decayed into helium-3. There was a guy named Ed Hamill at Los Alamos that was responsible for keeping their tritium supply clean, and that meant sorting out the helium-3. And then, without getting permission from anyone to do this, he decided that he would liquefy the helium-3 and measure its vapor pressure as a function of temperature. And he did that, and he published the results. And not only did he publish the results, but he said how much helium-3 he had. that told the Russians something about how much tritium the United States had. But he didn't lose his job. I interviewed him. He was 81 years old. It was a telephone conversation. And I wished I'd met him because he was a very colorful character. Anyway, there was a Russian theorist who was a member of what's called the Landau School, with very broad interests. And when he heard about helium-3, he started thinking about its properties. Now, helium-3 liquid at low temperatures, the entropy or disorder drops linearly to 0. So this is the entropy of liquid helium-3. Solid helium-3 is perfectly ordered spatially, but each nuclear spin can point either up or down in a magnetic field. That gives you an entropy of R log 2. And so below the temperature where these two curves cross, you have the very unusual situation in nature that the liquid is more highly ordered than the solid of a substance. I think this is the only case where that actually happens. And then Isaac Pomeranchuk was the Russian theorist, realized that so the helium-3 has a negative melting curve because of the fact that these two cross. And if you start with liquid helium-3 and you compress it and you start solidifying it, as you move along this melting curve, you move to lower and lower temperatures. So this was a technique that people predicted would allow you to reach temperatures probably less than 1,000th of a degree above absolute zero. And as a young graduate student, I said, I want one of these things. And so we had enough helium-3, and I built a very elegant, this is my Pomeranchuk cell, as it's called. So this gold region is helium-3 because it's rather expensive, I suppose. And the idea is you push metal bellows in here that decreases the volume and raises the pressure until some of the liquid starts converting to solid. And for every % of the liquid that converted to solid, the system would cool by 1,000th of a degree. What that meant was that if I converted 15% of the liquid to solid, I would be at a temperature very close to absolute zero. So that was the technique which I was pinning on my hopes on in order to get a PhD out of the low temperature group at Cornell. So here, in fact, is some data. Now, this is taken, you have to explain these things because young people now don't understand strip chart recorders. So the paper moves underneath a pen, which moves back and forth according to what voltage is applied to it. And so, in fact, this is the melting pressure of the helium-3 as it's cooling. And I'm actually measuring a pressure transducer made with a capacitor. So this is actually the capacitance, and I rebalance the bridge, and it continues to cool. And then there was a very sharp decrease in the rate of cooling, which I later labeled it A, but I was in fact quite crushed to see this because I felt that something had gone wrong, and so I let this continue to cool. And then I saw a little tiny drop in pressure at I wasn't very, shall we say, creative. I didn't give these things good names. A and B is what they were called. And in fact, this is the A superfluid, and this is the B superfluid, helium-3. So those names have actually stuck. But this was done this was actually not the first time I'd seen these things. I went back and looked at my old data, and there they were. So it was actually the pressures where these occurred were very highly reproducible. And so I suddenly realized, in fact, that, you know, this is something really, really exciting is going on. And so let me see if we have it. I invented a form of MRI where I actually applied a horizontal magnetic field that was larger at the bottom than the top. And so then if I applied an RF frequency, I would get a resonance layer such as I show here in red, and if I swept that frequency upward, this resonant layer would move down. So I could actually measure the NMR properties of the mixture of liquid and solid helium-3 as a function of position inside my cell. And so these are what some early data looked like. This is all liquid. There was this funny feature here was because the pressure transducer itself was slightly magnetic. And then we start cooling, and this is solid helium-3 started growing, and it gets larger and larger. And I have to change the gain, so the liquid looks like it's getting smaller, but in fact it's staying the same size. So this is real data. This was taken on April 17th, 1972, and I was looking at this data later on while I was waiting for things to happen, and this is the liquid signal. Should have been flat across here, and it looked rather badly distorted, and so I knew exactly what that meant. I wrote in my lab book, oops, yeah, here we go, 2:40 in the morning. This is a very good time to do research. No one bothers you at 2:40 in the morning. There's less radio frequency interference, there's less vibrations. It's the time to do research. So I wrote in my lab book, have discovered the BCS transition in liquid helium-3 tonight. And BCS is the theory that explained superconductivity. Bardeen, Cooper, and Schrieffer are the three theorists that did that. And people had predicted that helium-3 might undergo a similar phase transition, but it had never been seen. So there it was at 2:40 in the morning. What could I do? I ran around the basement of the physics building to share this exciting news with other graduate students. Well, it turns out no one was there. So in desperation, I went up to the 6th floor. The theorists, you see, like to be as close to God as possible. So they in fact would normally inhabit the 6th floor, but it turns out on that particular night there was no one around. And at 4 in the morning, I couldn't stand it any longer. I called up my thesis advisor, Dave Lee. Now, there are young people in the audience, so let me say that you do put your life in your hands if you call up your thesis advisor at 4:30 in the morning. However, in this case, David Lee called me back at 6 a.m. He'd not been able to get back to sleep, so neither one of us got any sleep that night at all. Anyway, I wanted to share this because it's I suppose not typical of the way science is done, but you get some feeling for the excitement associated with discoveries. So here I have some strategies, and this is really from another talk, but so utilize new technologies to view nature from a new perspective or a different realm. Now I'm talking about MRI, using the magnetic field gradient. Don't give up when things are going badly. Failure might be an invitation to try something new. I didn't tell you this, but to do the NMR experiments, I obviously needed a magnetic field, and the magnet that produced that field weighed about 5 tons. And we only had one of them, and some other students had gone to David Lee and complained that I'd been monopolizing this magnet for quite a long time. It was only, and then Dave Lee told me I had to give up the magnet, and so then I felt really, really bad. But in fact, it was that next evening that I did the experiment that discovered superfluidity in helium-3. So failure might be an invitation to try something new, and that's what I did. Spend a little of your time doing something different. Curiosity-driven research is fun and can be rewarding. And so as a thesis advisor at Cornell University, I would come up with, what would happen if I did this? And then if I thought it was interesting, I'd go to the graduate student and say, what do you think would happen if you did this? And they said, we don't know. I said, well, why don't you try? And in fact, that's a very typical way of making discoveries. Avoid too many commitments. Now, I have to say that I was married by this time. My wife is Chinese, and she was working very hard to teach me Chinese, but I'm a very bad student. And so Cornell University was offering a course in conversational Chinese, and we both thought it would be great for me to take this course, but voila, I laughed myself to death. I realized that in fact I didn't have the time to take this course. So instead, I never learned any Chinese, but I did get a Nobel Prize. So that was the booby prize for not having gotten your first choice. Anyway, and then finally back off from what you're doing occasionally to gain a better perspective on the task at hand. And I think this is absolutely true. We become myopic when we focus too tightly on our work. And I don't know how many young people are in the audience, but I think it's good advice. Okay, so this is David Lee, yours truly, and Bob Richardson. You can't see mine very well, but I didn't bother doing that. They still gave me the prize, though, which is good. So now I go back to this Pomeranchuk cell, and I put the names of people who didn't necessarily give anything for making Pomeranchuk cells particularly, but in fact, whose contributions to science in general, without them, I would not have made the discovery I did. So Bardeen, Cooper, and Schrieffer were the ones that developed the theory that explained superconductivity, and that theory was then applied to helium-3 by Phil Anderson, a very dear friend of mine. And of course, Pomeranchuk's cooling cell was why I was able to get cold. But in fact, to use Pomeranchuk cooling, you actually had to get to very low temperatures, and I used a helium-3, helium-4 dilution refrigerator, which was invented by Edwards and Hall to do that. Bloch and Purcell, I used NMR extensively in my research, and thanks to Bloch and Purcell, NMR had been developed. And then Ed Hamill was the one that gave the world helium-3 by not throwing away this helium-3 that he separated from the tritium. So it is certainly not me alone that did this work. There were a myriad of people that were associated with this. And this is the way science actually works. And the wonderful thing about it is once the work is published, it's out there and anyone can use it in any country they want to use it. So science is, in fact, an international occupation, and it's something that's shared very, very easily and in a very friendly way between nations. So advances in science are seldom made by individuals alone. Let me make that clear. It looks like I did everything, but in fact, there are all those names up there. Those were people that gave contributions that I needed. They result from the progress of the scientific community, asking questions, developing new technologies to answer those questions, and sharing their results and their ideas with others. To have rapid progress, one must support, now this is for funding agencies, but I think I always have to remind funding agencies that they're important. To have rapid progress, one must support scientific research broadly and encourage scientists to interact with one another and to spend a bit of their time satisfying their own curiosities. This is how advances in science are really made. Thank you. But we're not done.